My name is Maolin, a PhD candidate at Nanjing University, and I'm advised by Yibiao and Yumi. It's an honor to speak at OOPSLA and to share our recent research. The title of my talk is Validating SMT Rewriters via Rewrite Space Exploration supported by Generative Equality Saturation. Okay, before diving into our work, let's start with some background. Okay, our work focuses on SMT solvers, the tools that are designed to solve logical constraints. And here is they take formulas written in the SMT lib language as input. And here is a very simple example. Here we declare a variable x of type integer, and we add a constraint x greater than 0. And finally, we ask the solver to check satisfiability. And the solver responds satisfiable for this case. And if needed, it can give a concrete solution like x equals 1. And over the past decade, SMT solvers have become very, very powerful. They now support a wide range of applications like program analysis and formal verification. And in fact, the previous presenters' great works are also made use of SMT solvers for verification, and showing just how broadly these solvers are applied today. And their impact is so large that the 2015 SM Programming Languages Software Award went to these three, one of the most widely used SMT solvers in the community. And in industry, SMT solvers are also everywhere. For example, Amazon calls SMT solvers a billion of times every day to help ensure the security of their system. And it clearly shows the solver reliability and quality are essential. So many researchers have contributed excellent works on SMT solver testing, but one part is often overlooked. That is the rewriter. And the rewriter isn't just important for SMT solvers. You will also find rewriters in other major software systems like GCC and LLVM, where they play very important roles in program optimization. Yeah. So what exactly is a rewriter? The rewriter is the engine that simplifies formulas. It applies a lot of rewrite rules to transform formulas step by step into forms that are easier for solvers' core engine to handle. Yeah. Developers of Satisfiability have even said improving the rewriter is as important as improving the solver's core decision procedure. And if the rewriter is buggy, the impact can be very, very serious. And here shows an example. This formula on the left it looks very simple, right? Yeah. But surprisingly, these three reports unknown for it, meaning it cannot decide whether the formula is satisfiable or not. And after a closer look, we found the root cause, a missing rewrite rule. Yeah, in fact, if we replace A inside an empty string with another empty string, the result is still an empty string. So the formula can be rewritten into the simpler form on the right, which the solver can easily solve. And this shows the missing rewrite can cause completeness issue in solvers. And to further investigate the importance of the rewriter, we conduct an empirical study. We examined more than 8,000 pull requests from the CVC5 project over the past 10 years. Surprisingly, about 14% of the pull requests were related to rewriters. And if we check their priority levels, around 18% of the rewrite-related pull requests were marked major or normal by developers. This aligns with the developers' views that enhancing the rewriter is very important. But despite its importance, testing the rewriter is difficult. Two main challenges stand out. First, how do we make sure our test inputs really trigger rewriting? Without broad coverage, some rewrite rules might never be exercised, so leaving hidden bugs undiscovered. Second, even if we trigger rewriting, how do we check correctness of the solver's output? To tackle these challenges, we propose a two-phase method. Phase 1, mimetic mutation. In this phase, we mutate the seed formula to match the left-hand side of rewrite rules so that more rewrite can be triggered in next step. And phase 2, deductive rewriting. Here we will use equality saturation to explore the rewrite space and generating many formulas that are semantically equivalent. Together, these two phases make it possible to thoroughly test the rewriters. And our method should rely on a set of high-quality rewrite rules. So, where do these rules come from? In our work, we use two main sources. First is the existing rules implemented in CVC5, collected by peer study. And second, synthesized rules generated by Ruler, which is rules that infers new rules from existing ones. The second source is particularly interesting because these rules may reveal new rewriting opportunities that solver developers may not have implemented yet. However, rules synthesized by Ruler may not be always correct under SMT semantics. So we design an automated validation process. So for each rule, we construct a corresponding formula to check whether the rule ever produces a contradiction. We then cross-validate them with multiple solvers. For example, for the first rule, 0 plus t equals t, we can check if there exists an t such that 0 plus t is not equal to t. If all solvers return unsatisfiable, the rule is valid. And now, let's take a closer look at phase 1, mimetic mutation. We start with a seed formula, and from it, we randomly select a subformula and modify it so that it matches the left-hand side of a rewrite rule. In this example, on the left is the original seed formula, and we mutate one subformula such as R, and the result is the formula on the right. At this stage, we don't guarantee semantic equivalence. We just increase the chance of triggering rewriting. Yeah. Phase 2 is deductive rewriting. Here we leverage a technique called equality saturation. We build an equality graph, also known as E-graph. And each dashed box here in the E-graph is an equivalence class, containing nodes that represent semantically equivalent formulas. Initially, each class may have only one node, as shown in the figure. And we then repeatedly apply rewrite rules. As we do this, the E-graph keeps growing, discovering more and more equivalent versions of the seed formula. And in fact, the E-graph shown on the left hasn't reached saturation yet. Saturation happens when no rules can further change the E-graph. At that point, we have explored the full rewrite space given our rule set. And once the E-graph is built, we can extract many equivalent formulas. And because these formulas are guaranteed to be symmetrically equivalent, we expect the solver to give consistent answers for them. And if a solver's output differs, we flag it as a potential bug. Besides, two more design details may be also worth mentioning here. First, equality saturation engines are typically designed for optimizations. That means they typically simplify formulas, not make them more complex. But in the context of testing, we also need rules like rewriting 0 to x times 0, which will introduce new variable. So we modify the equality saturation engine to support this kind of rewrite. And second, we design a sampling strategy for extracting formulas from the e-graph. We give high priority to variants that are structurally different from the original one. This may allow us to trigger more rewrites and improve our ability to find bugs. And if you are interested with these technical details, please check our paper for more information. And finally, we implemented our approach as a practical testing tool called Arrays. We evaluated it on two state-of-the-art SMT solvers, Z3 and CVC5, using the seed formula from the SMT lib official benchmarks. And here's the result. Our tool found 27 unique issues, and 22 were confirmed by developers, and more than half have already been fixed by developers. These issues covered correctness, crashes, completeness, and performance. By checking developers' fixes, we confirmed that most of the issues were indeed rewrite-related. And this showed our method effectively targets the rewriter. We also ran an ablation study to evaluate the contribution of each component in our tool in terms of triggering rewrites. We built three variants here, one with only phase 1, one with only phase 2, and one with only the rules generated by ruler. In all cases, effectiveness dropped significantly compared to the full method. This confirms that all components are necessary for our approach. And finally, let me show a very simple case discovered by our tool. Here, this will return the unknown for the formula on the left, but the formula is always true. It indeed checks whether the empty string is lexicographically less than or equal to another string. So the formula could be rewritten to the simpler formula on the right. And we report this issue, and these three developers accepted our suggestion to add a new rewrite rule for it. And this shows our tool not only find bugs, but also directly help developers improve their system. And that's all. Thanks for your listening.
Do we have a very quick question? Yeah.
Hi, thanks for the talk. When you use equality saturation, do you test multiple rules at one time or just one?
Multiple times. Yeah.
Multiple?
Yeah.
So if you find a fault, how do you know which rule is faulty?
Actually, we have designed a very simple debugging process, also utilized equality saturation. And we, considering the time limitation, I don't introduce our approach here. If you're interested, you can check our paper.
Yes,
yeah,
okay.
Yeah.
Thank you.
Thank you for your question.
All right, thank you very much. That closes this session.